This is the second in our series of lectures on section 1.4. In this video, we're going to give some examples of working definitions. Okay, here are two definitions for you. The first one says, an integer a is said to be even provided there exists an integer n such that a is equal to 2 times n. And here I've written that definition in symbols. And we say that an integer a is said to be odd, provided there exists an integer n such that a is equal to 2n plus 1. And here I've written that definition in symbols as well. So I want you to forget about any prior notions you have about the ideas of even and odd. You may have other ways that you may think of defining those two concepts. But from here on out, these are the definitions of even and odd. Now, I don't want you to get hung up on the names that you see here. So you'll see the name A and you'll see the name N. So those aren't important. We can use the definition with different names. For example, if we have some integer b and we happen to know that it's even, then according to this definition we could say there exists an integer, say m, such that b is equal to 2 times m. Okay, we don't have to use these particular letter names. For example, suppose we have some integer a that we've written as 2 times n, but now we have some other integer b, and we happen to know that it's odd. Well, we're not going to say that that b is equal to 2n plus 1, because we've already used up the name n. And so we would have to say, there exists an m, such that b is equal to 2m plus 1. Okay, so you must never use the same name for different objects. Let me show you 3 ways that we can make use of a definition. And I'll illustrate this with the concept of even. So the first thing that we can do is we can use the definition to verify that a specific integer is even. So for example, how do you know that the number 18 is even? Well, we would go back to the definition. I like to look at it in symbols, and we'll take 18 to be our a, and we have to ask, does there exist an integer n? Does there exist an integer n such that 18 is equal to 2 times n? Well, the answer is yes. 18 is 2 times 9, and 9 is an integer. And therefore, according to this definition, 18 is even. Or as another example, is the integer 0 even? Okay, so replace a by 0 and ask yourself, does there exist an integer n such that 0 is equal to 2 times n? Well, yes, it's true, because 0 is equal to 2 times 0. So we could take n to be 0, and that would verify that the definition is true. And so 0 is even. Now, the second way that we can make use of a definition is, say we have an integer z, which we know already to be even. Well, then we can make use of the definition to write z in a different way. In other words, the moment we know that z is even, then we have the right to say, well, therefore there exists an integer, say n, such that z is equal to 2 times n. And that might turn out to be useful in the particular proof that we're doing. And a third way that we can make use of the definition is, say we have an integer w, and we don't know that it's even, but we want to prove that it's even. So in that case, we could go back to the definition and verify that it's true. In other words, we would have to prove that there exists an integer n. So we'd have to produce an integer n such that w is equal to 2 times n. Okay, if we were able to do that, then that would prove that our w is even. So those are 3 ways in practice that we actually make use of definitions. Well, I'm going to finish this video by showing you one more definition that we'll make use of in in future proofs. So here's a new working definition for you. In this definition, we're defining the concept of one integer dividing another integer. So we let m and n be two integers, where m is a non-zero integer. We say that m divides n, provided there exists an integer q such that n is equal to m times q. And here I've written that definition in symbols. It's easier on the eyes and easier to verify when you see it in symbols. So we say that m divides n provided there exists an integer q such that n is equal to m times q. And there are other ways of referring to these, other words that we can use. So we also say that m is a divisor of n, m is a factor of n, and we also say that n is a multiple of m. And a very commonly used notation is this one here. When we put m vertical line n, that's a shorthand for saying that m divides n. And you'll notice that in the definition we've taken m to be non-zero. In other words, we simply don't define the concept of zero dividing anything. Okay, so this is sort of a long definition, but really the most important part is contained in the first two sentences. So it's important that you remember what it means to say that m divides n, and if you just remember this part here, then you'll be in a position to make use of this definition in any of those three ways that I mentioned on the previous slide. It's very important that you memorize these working definitions. So far we've written down 3 working definitions, and by the end of the semester there will be many, many working definitions for you to know. And the point is, if you don't know your working definitions very well, you won't be able to write good proofs. Okay, it's absolutely crucial that you learn your working definitions.